In the middle of a quarterly operations review at a mid-size enterprise, the finance lead brings up the latest AI cost dashboard on the screen. The numbers look razor sharp. Inference usage broken down by the token, storage charged by the gigabyte hour, hosting fees scaled precisely to whatever is running at that moment. You can almost feel the quiet satisfaction settling over the room. Here, finally, is the kind of transparency that finance and operations teams have long hoped for, the sort that traditional automation systems never quite manage to deliver. The assumption feels reasonable and even reassuring. Leaders should now be able to see exactly where every dollar is going, assign costs confidently to the right processes, and adjust spending fluidly as business conditions shift from one quarter to the next. But later, when those same figures are reconciled into the full profit and loss statement, something all too familiar occurs. The total spend comes in noticeably higher than the sum of those clean, itemized line items, and the dashboards themselves offer no obvious explanation for the shortfall. That small yet recurring gap raises a quiet but important question about the real cost mechanics of artificial intelligence. Why does the apparent transparency of metered usage so often conceal deeper structural realities that only become visible once the numbers reach the broader financials? On the surface, the architecture does appear deliberately designed for clarity. Modern AI infrastructure runs on highly granular, usage-based billing. Every computation performed, every piece of data transferred, and every output generated carries its own visible price tag within the portal. Compared with heavy capital equipment locked into multi-year depreciation schedules or enterprise software contracts hidden behind opaque licensing terms, this feels refreshingly straightforward and controllable. The promise is intuitive. Track cost per unit of work with precision, trace expenses directly back to the specific business activity driving them, and maintain real-time visibility that supports quick, confident adjustments. Yet that comforting sense begins to fray once the system moves beyond small, contained pilot projects and into sustained everyday operations across the organization. A straightforward way to visualize this is to picture two vertical bars placed side by side. The bar on the left stands narrow and neatly segmented: direct inference costs, storage allocation, and hosting fees. The bar on the right shares that same slim, visible top, but rests on a noticeably wider base underneath. That base includes pipeline upkeep, integration effort, ongoing monitoring, shared resource amortization, and the coordination required to keep the system stable. The sketch isolates the central tension. What appears on standard billing statements looks complete and auditable, yet depends on a broader foundation that is neither fully itemized nor easily observed in real time. That foundation reveals the real limitation. The system's economic footprint extends well beyond metered usage to the continuous work required to preserve reliability. Data pipelines need ongoing refresh and validation to prevent drift. Models must be monitored, retrained, and versioned as conditions change. Edge cases accumulate and demand handling. These activities consume compute, storage, and specialized labor, but they rarely appear as discrete, attributable costs on the primary billing interface. What looks like precise usage accounting captures only the execution layer, while the operational layer that sustains it remains distributed and only partially visible. Even when organizations try to account for this broader layer, allocation adds further difficulty. AI systems are typically built on shared infrastructure that serves multiple functions simultaneously. A single model may support customer-facing features, internal analytics, and risk processes within the same environment. Total resource consumption can be measured with reasonable accuracy, but mapping that consumption cleanly back to individual business units or workflows proves far less precise. The same compute capacity shifts across use cases over time, and the supporting infrastructure does not segment neatly along organizational boundaries. As a result, the challenge moves beyond incomplete visibility of total cost to the difficulty of assigning that cost in a way that aligns with internal financial accountability. At larger scales, this dynamic grows clearer still. What enters the system as variable, usage-based charges gradually takes on characteristics more commonly associated with fixed commitments. Maintaining uptime requires redundancy. Ensuring performance stability demands continuous background activity. Security, compliance, and governance introduce persistent overhead. Specialized teams must remain in place regardless of short-term fluctuations in usage. These elements do not expand and contract in direct proportion to token counts or storage metrics. Instead, they create economic stickiness, where portions of the cost base cannot be reduced quickly without affecting system reliability. In contained pilot environments, the hidden layers stay relatively small, so the system behaves close to its metered representation. But as adoption broadens across workflows and volumes increase, those underlying dependencies expand and the overall structure shifts towards something more complex and partially fixed. The apparent transparency holds only within a relatively narrow operating range. Organizations often respond by building more sophisticated internal accounting mechanisms, tagging resources by project, layering internal labor onto provider costs, and developing attribution models to distribute shared expenses more systematically. These approaches can improve directional clarity and support better decision-making. Even so, they do not fully resolve the underlying tension. Because these systems operate across shared data flows, infrastructure, and human oversight, some portion of total cost will always resist precise, real-time isolation, regardless of how detailed the tracking becomes. In the end, this persistent difference between what the dashboards comfortably display and the fuller structural cost picture plays a quiet but decisive role in how companies evaluate and sustain their AI-related capital commitments under normal operating pressure. Teams that accept the visible numbers as the complete story risk underestimating the true economic burden of keeping these capabilities operational at meaningful scale. Those who factor in the broader architecture, including its hidden dependencies and allocation frictions, tend to arrive at more grounded and durable decisions. They come to see the supporting layers not as optional overhead, but as integral parts of the investment itself. In practice, the distinction between cleanly metered costs and those that remain embedded tends to endure even as deployments mature. Organizations that handle this well develop disciplined routines for reconciling external billing data with internal spending patterns and quarterly results. These efforts rarely produce perfect accounting, yet they gradually sharpen judgment about the true durability of AI-related commitments. What emerges is a more realistic view of capital allocation, one that accepts partial visibility as a permanent condition rather than a flaw to be solved. Understanding these persistent frictions matters as much as understanding the advancing capabilities of the technology, because it is precisely at that boundary between metered visibility and structural economic reality that so many thoughtful AI investments quietly encounter their most stubborn and enduring constraints